Hello guys, this is section 2.2, Newton's laws of motion. We're going to talk about three laws of motion, pretty much similar to what we already learned in grade 11. First Newton law is very connected to inertia. That's why sometimes we call first Newton law of inertia. Inertia is a property of matter that causes it to resist changes in motion. Inertia is directly proportional to a mass of the object. That's why it's more difficult to start or even to stop moving a more massive object compared to the smaller object. Now, in order to understand the inertia, we should take a look at this diagram. Explain what happened in this picture. So why a person's body is moving backward when a bus starts moving forward? Because the object tries to stay where it is. Inertia comes from Latin word that is laziness. So the objects are lazy to change that motion. If they are moving, they will continue to move. If they are stationary, they want to stay stationary. So that's why when the bus starts, our body, we're used to stay at stationary position. So when a bus moves forward, we want to stay as it was before, backward. That's why our body is moving backward. As a matter of fact, it's not really moving, but it's staying at that position that was before. So it feels like it's moving backward, but it's not moving backward because a bus is taking us forward. Since that head is free to move, that's why head is moving backward. It's moving backward, so it's staying at that previous position. The same thing is if the bus is stopping. So that means that we were already moving and we want to continue to move. Bus is stopping us to move, but head that is more free to move, it is keeping that same pace as before. So that's why it looks like that our head is moving forward, but actually it is keeping the same pace as it was before. Here's a thinking experiment. If you are in a plane and plane is flying horizontally at constant speed, and you have a tennis ball in front of you on the top of the table, tennis ball does not move horizontally. Why? Because it's moving at the same rate as you're moving, the table is moving, plane is moving. So there's no reason to change that pace, that constant motion. However, if the plane rapidly gains or accelerates forward, so the tennis ball will move toward the back of the plane, keeping the same pace as before. So it's trying to resist the change in velocity. So now you'll see that relative to you, that ball is approaching you. As a matter of fact, ball is not approaching you. Ball does not really change that state. Ball is trying to keep the same way as it was moving before. In the same way, your body will react while sitting if the bus is speeding up or slowing down. So it changes the motion. So when the object changes the motion, there is a inner resistance to keep moving at exactly the same pace. So that's why your head is actually leaning backward if the bus is start accelerating forward, or your head is leaning forward if the bus is stopping, so it's slowing down. And this happened all because of inertia. Inertia is a property of matter that causes it to resist changes in motion. Inertia is directly proportional to the mass of the object, And that's why it is more difficult to start or stop moving a more massive object compared to a smaller object. Any object will behave the same, and see if that motorcycle suddenly stops because of the wall. Your body is going to just keep moving forward as it was moving. The same way is that if the car suddenly stops, that means that a driver, if it is not wearing the seatbelt, is going to fly through a window. So that means that the driver will keep moving as it was moving before. So to protect the driver in a case of accident from flying through the window, through the windshield, that's why we use a seatbelt, to restrain that sudden motion, to restrain. Isaac Newton studied inertia and came to a conclusion that if net force on an object is equal to 0, or F net is equal to 0, or sum of all forces is equal to 0, then the object is in equilibrium. So that means the object is in a static equilibrium when it is at rest. So velocity is 0. That means acceleration also is 0. Or the object is in a dynamic equilibrium when it's moving at a constant velocity. So when a velocity is constant, that means there's no change in velocity. That means the acceleration has to be 0. So in both cases, acceleration is 0. The law of inertia is now called Newton's first law of motion because it's included with Newton's other laws of motion. Newton's first law of motion is about equilibrium. It says if the net external force of an object is 0, the object will remain at rest or will continue to move at a constant velocity. So for short, we can write if F net is equal to 0, or if sum of all forces is equal to 0, then velocity is 0 or velocity is constant, or acceleration is 0. An object that obeys first Newton law is in equilibrium in one dimension or even in two dimensions. And we can write F net is equal to 0. That means that F net on the x-axis has to be 0, and F net on y has to be 0 as well. Or we can rewrite it with the sum of forces is the same thing. Sum of all forces equals 0. That means sum of all forces on x-axis has to be 0, and sum of all forces on y-axis also has to be 0. This is an equilibrium practice problem, first Newton law. For the diagram on the right, what is the magnitude and direction of the force necessary to produce equilibrium? So it's a missing force because we do not know magnitude and direction, so we cannot draw it. The first step would be to draw a coordinate system, x and y, and label it. And then label forces and resolve forces into components by drawing perpendicular to x and perpendicular to y lines from the tip of each force. Then draw and label component, and we're ready to calculate x and y component of each individual force. So F1x is equal F1 cosine 60 is 8 cosine 60 is equal 4 Newton, but it's negative because it's opposite direction of the positive of the x-axis. F1y, it is F1 sine 60, which makes plus because it is up, it's positive is up, it's a plus 6.93 Newton. F2x is F2 cosine 30, is a positive, so it's a 4.33 Newton. And F2y again is positive because it's in the first quadrant. Both of them are positive. F2 sine 30, which is 2.5 Newton. Then we can add all x component together, sum of all forces on x is equal to 0. So F1x plus F2x plus F3x. F3 has a 0 because it doesn't have component on x-axis because it is on a y-axis. And F4x, it is unknown, so we can leave it as it is. And we can plug those numbers with sign, with a direction. It's very important, direction. Then we get F4x is equal minus 0.33 Newton. And we label it and draw it. Next step would be what happened on a y-axis. We do the same thing. Sum of all forces on a y-axis is equal to 0. And we can just replace F1y, F2y, F3y, F4y. Okay, so then we can solve for F4y, which is minus 0.43 Newton. And we draw it. After we draw it, we draw F4, which is a hypotenuse, and the angle theta. And we can calculate hypotenuse based on Pythagorean theorem. So it's a square root of 0.33 squared. That minus doesn't really matter because it's squared anyways. Plus 0.43 square will give you 0.54 Newton. And then we're ready to calculate for theta angle. And that angle is tan negative 1 of 0.43 divided by 0.33. That is 52.5. So now we have magnitude and we have a direction of the missing force that can produce equilibrium. If we draw that on a diagram, then surely everything will be in equilibrium. Before we can start second Newton law, let's review first Newton law. The first Newton law of motion applies to a situation when sum of all forces or net force is equal to 0. So we have either an object that is at rest will remain at rest, so velocity is going to be 0 and it will stay 0, or object that is in motion will continue to move at a straight line at a constant speed, or the constant velocity is going to happen, so velocity will not change. In both cases, since the velocity is not changing, acceleration is 0. What will happen if the F net is not 0? What will happen if we apply a force, an unbalanced force on an object? The answer will be object will accelerate. So at what rate? At what direction? Those questions can be answered if we do few experiments. As in any science experiment, we have variables, and we keep some variables constant while we're changing other. So we change one variable at a time to see effect of that variable to the process. That's what we do here. If we want to analyze the effect of the force in acceleration of the object, we keep the mass the same. So mass constant. And here's the experiment. If the force acting on the same card, same mass, will increase, then acceleration will increase. So you see on the first, it's a card with a small mass, and we increase the force and acceleration will increase. Now, to explain that in a real life situation, we have two cars with the same, almost the same mass. The car with a powerful engine will accelerate faster, and there's no doubt the race car has a very powerful engine, while they have almost the same mass. If we graph force and acceleration, the graph would look pretty much like this, with a straight line that goes through origin. The slope of that line is representing mass of the object. And obviously it's a straight line because slope of the straight line is constant and mass is constant, is not changing. Now the line must go through origin because acceleration is 0 if net force is 0. If we do an experiment, similar experiment with the same mass, with a constant mass, but now that card is on an air truck, which is going to minimize the friction. That's what air truck is about. So on those holes, the air will blow. So to make that car to kind of float, to minimize the contact, to minimize the friction. So you'll see the effect purely how the force will affect acceleration. If we apply a force, then we'll get an acceleration. However, if we double the force, we'll get a double acceleration for the same mass. If we want to analyze the effect of the object mass in the acceleration of the object, we can keep force the same or almost the same. So the force is constant. The force acting on a card with a small mass will accelerate faster, while the card with a bigger mass will have a hard time to accelerate, will accelerate slower. And you have noticed that at the shopping cart. So when you go to the grocery store and you use the shopping cart at the beginning, it's so easy to move it from stationary state to a moving state. However, when the cart is full of stuff, it is harder to start it moving, to push from rest to start moving. And the same thing is if we compare two engines in a different masses. So the race car and the truck almost have the same powerful engine. However, race car has much lower mass compared to a truck. And obviously, race car can pick up speed right away and it accelerate much faster than a truck. So if we keep the force the same or almost the same, the force acting on a cart with a small mass will accelerate faster. If you graph acceleration versus mass, the graph shows a reciprocal relationship like that. And if we do the experiment again with an air truck and a cart being pulled by the same force, a constant force, you're going to see for the first mass, the acceleration is going to be A, but for a double of mass, acceleration is going to be half. So you see a relationship between mass and acceleration is inversely proportional. Newton's second law of motion says that if net external force acting on an object is not zero, the object will accelerate in the direction of the net force. The magnitude of the acceleration is directly proportional to a magnitude of the net force and inversely proportional to a mass of the object. So mathematically, we can express the second law of motion in this way. Acceleration, it is equal to a force divided by mass. And you see the direction of the acceleration, it is in the same direction of the force. Or we can say force is equal to mass times acceleration, and that is useful to figure out what would be a unit of the force. Since the mass is 1 kilogram, unit of mass is a kilogram, and unit of acceleration is meter per second square, we can say that 1 Newton is equal to 1 kilogram times meter per second square. Here is a practice problem that involves direction of the acceleration. In which direction does the object accelerate? Explain. Let me explain. I'm going to explain by saying why those options are not an answer, are not true. Let's start with the A. A is not true because if that was true, then F1 and F3 has to cancel each other, which make F1 and F3 the same magnitude, but in opposite direction, which is not true because F3 is longer than F1. So we do have a vertical component, vertical resultant. B is not an answer because for the same reason. If the F1 and F3 has to add up together, will produce a resultant downward, not up. So the B would not be an answer. C is a nonsense option. There's no way that C would be an option at all. And E is not true, not correct, because you cannot ignore F2. If the F2 would not exist and we have only vertical forces, then E would be an answer, which in this case it is not because F2 exists. So the only correct answer is D. D because the resultant of F1 and F3 would produce a vector that is downward, and if we add vector F2 and sum of F1 and F3 would be something that in that direction of A. This is a simple practice problem with second Newton law. A 64 kilogram runner start walking at a 3 meter per second east and begin to speed up for 6 seconds, reaching a final velocity of 12 meter per second east. Calculate net force acting on a runner. Here what we have is a mass 64 kilogram, initial velocity 3 meter per second east, final velocity 12 meter per second east, and time interval is 6 seconds. Calculate F net or sum of all forces. It's the same thing. We use sum of all forces sometime in grade 12, but exactly the same. So F net is equal M times A. Acceleration, you can use kinematics. It's V final minus V initial over delta T. So 12 meter per second east minus 3 meter per second east. So direction east are the same, so we can do it, calculation. So it is 15 meter per second divided by 6 is equal 1.5 meter per second square east. Then we're ready to calculate F net or sum of all forces. It is equal M times A. 64 kilogram times 1.5 meter per second square east. The force is 96 Newton east. Here is a similar problem, but now is a slowing down. During the road test, a driver brakes a 1,420 kilogram car moving at the 64.8 kilometers per hour west. The car slows down and it comes to a stop after moving 729 meters. Calculate the net force acting on the car. I want you to pay attention to these units because it's very important. 1420 kilogram is a standard unit, but 64.8 kilometers per hour is not. And now the distance or displacement is 729 meters, which is a standard unit. So the first thing we need is to convert it. Initial velocity is 64.8 kilometers per hour, which makes 18 meters per second. So in order to calculate F net is equal MA. So we have final velocity 0, which is the car come to a complete stop. Displacement is 729 meters west. And in order to make it easier, we can make west as a positive, since we have both west and west. So acceleration is 0 minus plus 18 meters per second square divided by 2 times 729, which is minus 0.22 meters per second square. So since that we actually use west as a positive, now if we reverse it, that is going to be east. So it's going to be 0.22 meter per second square east, which makes sense. Now we can calculate F net is equal to m times A. It's a 1220 kilogram times 0.22 meter per second square east. That will make 315.6 Newton east. As a matter of fact, if you want to go over and make sense out of this problem, you'll see that when a car starts braking, the force of friction slows it down. So that means force of friction has to be opposite direction. So acceleration has to be in opposite direction of the previous direction of the motion. So that's why car is moving toward west, and acceleration, which is slowing down acceleration, is in the opposite direction. It is toward east. So that's why the force of friction is always against the motion, and now it is 315.6 Newton against the motion, against opposite of west is east. So that makes sense. Solving a Pulley problem is very long and complex, and I want you to pay attention to this one. Pay attention to steps because they are very important to help you not to get confused and not to make mistakes. Calculate the acceleration of the cart and the tension on the rope. Given the following assumption, there is no friction acting on the cart. The first thing that you can do is to label the masses, tension, and acceleration. Next one is write what is given, what is required. Mass 1 is 1.2 kilogram, mass 2 0.6 kilogram, and acceleration and tension is required. As solving any dynamic problem, you have to draw free body diagram. Let's start drawing a free body diagram of object 1, the cart. So object 1 is a force of gravity. Label it 1. Make sure you don't forget that. It's a normal force acting on the cart. And there's a tension pulling the cart on the right, and that will be a positive direction. So the direction of the motion is the direction of the acceleration, and is a direction that we label it as a positive direction, regardless it is left or is right, is up or is down. So choose the positive direction and apply the appropriate Newton's law on each axis. What does this mean? That means that you can apply first Newton's law if there is no motion on that axis, or is motion at the constant velocity, which in this case is not true. Or you can apply second Newton's law when there is acceleration. So in a first Newton's law, we can apply on y-axis because we know the cart is not moving up or down, it's moving horizontally. So F net has to be 0. So F net is sum of all forces. In this case, we have 2. Fg1 and Fn1. We can follow the positive direction, and positive direction, since that is a first Newton's law, we're going to keep it traditional, positive up. So Fn is in direction of the positive, so it's going to be positive, and Fg1 is opposite of positive, so negative. Now we have Fn1 is equal to Fg1, and we're going to leave that here However, when we're going to study friction on chapter 4, we will use Fn. But for now, we're not going to calculate anything. Just leave it. Now, F net x is equal to m1a, is object 1, is a mass 1, is accelerating in that direction. So F net is equal to sum of all forces on x-axis, which we have only one force on x. So F net x is equal to T1, that is equal to m1a. So we can follow the positive direction. We can say T1 is positive and acceleration is positive as well. So we can write equation number 1 as a T1 is equal m1a. So plus T1 is equal plus m1a. We'll continue with the solution. Now we're going to focus on object 2. If you take a look, the acceleration regarding to object 2 is downward. So that's why we label that direction of the acceleration as a direction of the motion. That's downward. Now we can draw and label the object 2 free body diagram. Object 2 free body diagram is simple because we have only one direction. It's FG2 and T1. The direction of the acceleration is down, so then we can use the second Newton law on that direction on a y-axis. So F net y is equal m2a, and F net y is the sum of all forces, which is Fg2 plus T1 is equal m2a. Now take a look. The positive direction is down, so Fg2 is positive and T1 is negative. So we can say Fg2 minus T1 is equal to m2a, and that makes equation number 2. Now next step would be add those two equations together, equation 1 and equation 2. Make sure we did not make any mistake, so both acceleration has to be positive. And another thing that you have to look is tension has to cancel. So Fg2 minus T1 plus T1, they will cancel. So on the left is a Fg2, and on the right we have m1a plus m2a. So a is a common, we can factor it. So there's a m1 plus m2. Now we can solve for a. So a is Fg2 divided by m1 plus m2. And we can plug those numbers in that formula, and we can find acceleration is 3.27 Newton per kilogram or meter per second square in that direction that is labeled. Now in order to calculate the tension, we go back to equation number 1, which is the easiest one. So tension is equal m1a. We do have m1 and we have a, so we can actually plug those numbers in the equation, and we find that tension 1 is 3.9 Newton. Now force of friction has to be taken into consideration when we calculate acceleration and tension. Let's start with labeling the same way. Object 1 and object 2, direction of the acceleration and tension. Write what is given, what is required, and then draw and label the object 1 free body diagram. The difference here is we do have force of kinetic friction, which is the opposite direction of the motion. So the motion is on the right, and force of kinetic friction has to be on the left. We choose a positive direction, which is direction of the motion, and for y-axis, which is not moving, it's no motion on y-axis, we keep it simple, traditional, positive up, and for x-axis, the direction of the motion is the direction of the acceleration, which is going to be a positive direction. Let's start with the first Newton law on a y-axis. Fn1 is positive. That's why it's is positive, because it is in a direction that we chose to be positive. And Fg1 has to be negative. Now on a y-axis, we're done. With the x-axis, there's an acceleration. So apply second Newton law, F net x is equal m1a. F net is equal to sum of all forces. In this case, we'd have two forces. Positive is T1 and negative is Fk. So T1 minus Fk is equal m1a, and that will be equation number 1. We will continue with the object number 2. We take a look. There's acceleration here that is very important to look. Acceleration is down, so will be a positive direction. We do pretty much the same way. So this object is not affected by friction at all. So everything that we did at A, it's at B as well. So Fg2, T1, direction of motion is down. That will be a positive direction. And then we apply the Newton's second law in y-axis. So F net y is equal to m2a, and F net y is equal sum of all forces. We have two forces on that y-axis. So Fg2 is going to be positive, T1 negative, and m2a is positive because it's the direction of the motion that we already chose. So Fg2 minus T1 equals to m2a, and that will be equation number 2. And the last step would be we add the system of two equations. You see that T1 will cancel. On the left is Fg2 minus Fk. On the right is m1a plus m2a. We factor a and we solve for a. So it's Fg2 minus Fk divided by m1 plus m2. We plug numbers on that formula and we find acceleration is 2.99 Newton per kilogram or meter per second squared. We can calculate tension on a string using equation 1. We move Fk to another side of equation, that minus Fk becomes plus Fk. And we plug numbers and we find T1 is equal 4.1 Newton. And that's end of the lesson. Forces always come in pairs, acting on a different object. For example, if the object 1 exerts a force F on object 2, then object 2 exerts a force minus F in object 1. So the same force, but in opposite direction. These forces are called action-reaction pairs. If we have two objects, two spheres, we know that if the object 1 applies a force on object 2, that we can label it F1 or on 2, then object 2 is going to apply immediately a force, the same force, same magnitude, but the opposite direction in object 1. Everybody might have played and blew a balloon and let it go. You're going to see, because of the rubber elastic force squeezing the air out of the balloon, if you don't tie up the balloon, air will rush out by pushing the air that is in the room, and in return the air is going to push that air that comes from balloon, and the air is going to be pushing the balloon itself, and that's why balloon is moving at the opposite direction of its opening. This is a starting point to build a rocket. How the rocket works. The gases on a rocket are action forces. So they rush out of the rocket, burning, and a hot gas that is burning is pushing the air, and in return, the force, a returning force, a reaction force, is going to push the rocket that is moving on opposite direction. Another easy way to experience action and reaction forces is by pushing on the board or someone else or on a wall when you're skating on an ice rink. So if you see on a picture, the picture on the right, that's a skater pushing on a wall. As the skater is pushing on a wall, the wall is pushing back, and that's why you see a reaction. You cannot see the reaction of the wall because the wall cannot move, but easily you can see a reaction of that force that you apply on a wall. So when you push on a board or any other object, that is an action force, but always there is a reaction force associated with action force. So the board or a wall or somebody else is going to push you back. So that reaction force causes you to accelerate away from the board or somebody else or from the wall. Action-reaction forces are simultaneous. These are contact forces, and both action and reaction forces start whenever contact is made. Third Newton's law of motion, action-reaction law, deals with this action and reaction forces. Here is a definition of third Newton's law. For every action force, there is a simultaneously reaction force that is equal in magnitude but in opposite direction, and we can write it as a F1 on 2 force of object 1 applies on object 2 is equal to a negative force that object 2 applies on object 1. So F1 on 2 is equal to minus F2 on 1. Here is a practice problem involving action and reaction forces. Two skaters are standing on an ice facing each other. Skater 1 pushes on skater 2 with a force 70 Newton. Simultaneously, the skater 2 will apply a force on a skater 1 with the same magnitude but in the opposite direction, minus 70 Newton. So we know that force 1 on 2 is equal to minus force 2 on 1. The question is, if both forces are equal in magnitude but in opposite direction, why do both skaters accelerate? In order to answer this question or any dynamic problem question, you have to draw what is mandatory for dynamics or forces, free body diagram. Now you understand that when you draw a free body diagram of each individual skater, on an x-axis we have unbalanced force. So we have F net. So F net on each individual skater or object in this case is not zero. As the F net is not zero on x-axis or horizontally, that means that both objects or both skaters in this case will accelerate. Since we know now that both skaters will accelerate, the question is, do skaters accelerate at the same rate? If mass 1, for example, is 50 kilogram and mass 2 is 65 kilogram. Okay, let's prove it. Force 1 on 2, so the object 1 on 2 is 70 Newton, which is equal to force negative of force 2 on 1, which is minus 70 Newton. Let's calculate acceleration of the skater 1 or object 1. So the force that is acting on object 1 is a force that object 2 applies on object 1. So F2 on 1, that's very important. Although that's the same, but that will show you the direction of the acceleration. So minus 70, the skater 2 is applying on skater 1, divided by 50 kilogram, that is skater 1, is equal to a minus 1.4 meter per second square. That's why skater 1 is going to move left. And if you do the same thing for a skater 2, that will be a force of object 1 applies on 2. So that's a 70 divided by 65 is a 1.08 meter per second square. So that means both objects will accelerate, but the rate of the acceleration will depend on their masses. And since the masses are different, acceleration has to be different. Here are some more examples of the third Newton law or action-reaction examples. So it's a person that is pushing the skateboard, and the skateboard in return is pushing the person forward to jump off the skateboard. Or if you have noticed those short races, running races, like 100 meter or 200 meter, since that they are 50, 100, and 200, since that they are short race, athletes always use a starting block. So how does that work? The block is fixed on the ground, and an athlete, when it starts the race, is pushing back the block, and in return, the block is going to push the athletes forward, so it can start the race. Why do they use, out of curiosity, why do they use that on a short distance races? Because since that it's a short distance, you don't have time to recover if you had a very bad start. So in these cases, we have application of third Newton law when we can say force of the object 1 is exerting on object 2 is equal to the opposite direction of the force that the object 2 is acting on object 1. You can name many examples actually of the action-reaction. We walk like that. We push the ground backward and the ground push us forward. We take it for granted, but that is an application of 13th Newton law. Cars moving like that. So tires is pushing the ground backward, and ground in return is pushing the car tires and the car forward. That's why in the winter you need to have a better tires, to have a better grip in order for that static force of friction that we're going to learn later on to be stronger, bigger, so that ground can apply a force on the car so that car doesn't slip off when it starts. Another way is if you try to push the refrigerator or something heavy, a wall that is not moving, you're going to see that reaction in your hands. You can try to push a cart and you're going to feel on that air truck, you're going to feel that is, you're going to have the reaction back. Action-reaction is the, as we mentioned before, is a force of gravity. So Earth is pulling the object, satellite, for example, artificial satellite or any object, down toward the center, and that object is pulling the Earth toward the center of that object. In the skater example, when the two skaters are pushing each other, or one skater is pushing other, and as reaction force is being pushed back, we know that although forces are the same, the acceleration will not be the same unless the object have the same mass because of the second Newton law. Here is a question. Will two objects accelerate at the same rate if we push them with the same force in a different direction as shown in the picture? So there are two blocks. The force that applies on a block is pushing block 2, and obviously block 2 is pushing block 1. And on the second one is force is applying on a block 1, and as a result, block 1 will push block 2. The answer is simple. Based on second Newton law, the acceleration, as I'm talking about magnitude of acceleration, has to be the same because it's the same force pushing the same total mass. So both blocks will act as a one. When they accelerate, they will accelerate at the same rate together. No matter where the force is applied to one block or the other, the small block or the big block, together they will accelerate at the same rate because of the total mass. Here is a tricky question. Is the action-reaction force between two blocks the same regardless of where the same force F is applied? So with the other way is, you know that if the force F is pushing object 2 and object 2 is pushing object 1, and in return the object 1 is pushing object 2, is that the same if the force is pushing a small object in the first diagram and a second object, the big object on a second diagram? Is that action-reaction between two blocks the same? So action-reaction between two blocks here is the same as action-reaction between two blocks here. This problem will answer that question raised that if the force, action-reaction force that is between two blocks is the same when a force, external force is pushing the bigger box or a smaller box. Here are some numbers. two blocks with a mass m1, 15 kilogram, and mass m2, 10 kilogram, are pushed together by a force 100 Newton. In this case is on the left, minus 100. Calculate acceleration and magnitude of action-reaction forces between blocks in a first diagram when a force pushes object 2, small 1. For acceleration, we know exactly what happened, but before we draw a free body diagram of both objects. If you take a look, the force F is applying on object 2 only, and on object 1, the only force is the force that object 2 is pushing it. So using a second Newton law, we can calculate acceleration, which is a force, net force divided by total mass, in this case. Then the total mass is 10 kilogram plus 15 is 25. Force is on the left is minus 100 Newton. So acceleration is minus 4 meter per second square. We can use this acceleration to calculate F net on object 1. It's easier because the only force on object 1 is that 2 on 1. So we can calculate it, and we find that the force that the object 2 is pushing 1 is 60 Newton. Okay, remember that value, 60 Newton, and we can continue with the next direction. If the force now pushes the object 1, we do pretty much the same thing, draw a free body diagram, although that will look slightly different, because on object 1 now we have two forces, and on object 2 the only force that is acting on object 2 is the object 1 is pushing it. So object 1 or 2. Same thing, we can calculate acceleration, which in this direction is a positive direction, but we are not focused on the direction because we know. So it's the same, it's a 4 meter per second square. And we can use that on object 2 because that's easier, because that's the only force acting on object 2 horizontally is a force 1 on 2, and we can solve for it. And the force 1 on 2 is M2A, which is 10 kilogram times 4 is 40 Newton. So if you remember that the force between two blocks were 60 when a force is pushing the small box, and now it's 40 when the object that is being pushed by a force is object 1. So it is not the same. It is not the same as you are accelerating or pushing a big object using a smaller object with a moving smaller object by using a bigger object as a push. So it is not the same. That's about it for action-reaction forces. I hope you enjoy it. In a 1.6, we talk about gravitational acceleration. Now the gravitational acceleration has a different name, but it is the same thing. Gravitational field strength. So gravity is an action at distance force that pulls an object without making any contact with it. To understand the gravitational field, we should know what a force field is. The force field is a region, is a space. So a region of space surrounding an object that can exert a force on other objects. The field exerts a force only on objects placed within that region that are able to interact with that force. Remember, the range of the gravitational force is infinite. So that means a field is infinite. Gravitational field is infinite. So no matter how weak that field is, there is a force acting on it. More about this you're going to learn in chapter 6 in grade 12. But for now, that is enough. Gravitational field strength is a force per kilogram of mass acting on object within a gravitational field. The symbol is the same thing as a gravitational acceleration, g, and value is the same, but the unit is a slightly different, although we did use it on section 3.3, 3.4, 3.5 on a previous chapter. The gravitational field strength is a vector quantity, as acceleration is the same thing. To represent the gravitational field around the Earth, we draw lines of force field that points toward the center of the Earth. As you see, those lines goes closer to the surface of the Earth and get closer together. That means that field gets stronger as you move closer to the surface of the Earth. As the magnitude of the Earth's gravitational field decreases as object moves further away from the Earth's surface. More about this we're going to learn on chapter 6. To determine the gravitational field strength at a particular location, you can measure the force of gravity acting on object and divide by mass of the object. So gravitational field strength is force of gravity divided by mass. The unit is Newton per kilogram, or kilogram meter per second square divided by kilogram. So kilogram and kilogram cancel. So the unit is meter per second square. So that is something that you know already. That is unit of gravitational acceleration. So gravitational field strength and gravitational acceleration are pretty much the same thing. If you see the diagrams on the right, it is very clear to see that Earth is not a perfect sphere. At the poles, at the object sea level is 21 kilometers closer to Earth center at the sea level compared to equator. So the difference of the diameter measured at poles is, if you see, is 42 kilometers less than diameter that is measured at equator. So 42 divided by 2 is 21. So that's a radius 21 kilometer less from poles to the center of the Earth. That means that gravitational field strength has to be stronger to poles than at the equator level. Here's a table where the values of the G will vary based on location. And as I said in chapter 6, you're going to learn how to calculate G using universal gravitational force in order to calculate the values of G at North America, which is 9.8. So we know that the mass of the Earth is constant, radius is changing. So that's why G is changing based on distance from the center of the Earth. In everyday language, terms mass and weight are used interchangeable. But these two words have different meaning. They are not the same. While mass is a quantity of matter in object, weight depend on mass but depend on gravitational acceleration as well. The only way to change mass of the object is either to add or remove matter. So weight or a force of gravity are the same thing. The weight of the object depends on location and the magnitude of Earth's gravitational field strength, G, or gravitational acceleration. So the weight is equal to the force of gravity is equal to mass times gravitational acceleration or gravitational field strength. So mass is different from weight. On the moon or on another planet, your weight is different, but your mass is the same. For example, The magnitude of gravitational field strength, also force of gravity or weight, on a surface of the moon is approximately 1/6 of that on an Earth's surface. On a diagram on the right, you see a mass 100 kilogram. It is the same on the moon's surface and on Earth's surface. However, weight on an Earth's surface is 980 Newton, while the weight on the moon's surface is 162.2 Newton. So mass of the object is the same everywhere. Weight of the object depends on location. Let's analyze the difference between what is the weight and apparent weight. Weight is the force of gravity, but apparent weight, because of the motion, the object appears to have a lighter or heavier weight. Now let's see what is a normal, what is a weight. As you stand on a bathroom scale, the magnitude of normal force is equal to force of gravity. Because you are not moving, that means that F net is 0. Based on the first Newton law, this would be the same if you are moving at a constant velocity, or as I said before, not moving at all. So F net is 0, and those two forces, normal force and force of gravity, has to cancel each other, so they must have the same magnitude. So if elevator is not accelerating, so it's staying at rest or moving at a constant velocity, we know that weight is exactly your force of gravity. You already have experienced apparent weight, so that means you are feeling heavier or lighter if you ride a roller coaster or if you ride the elevator. So if an elevator accelerated upward, then you see that you feel heavier because normal force not only has to fight the gravity, but has to accelerate you upward. While the elevator is accelerating downward, then normal force have an easy way accelerating you downward because the gravity is helping you. Let's say that you're free falling. So elevator or any way, you are falling at a rate of acceleration. So you are accelerating downward at 9.8 meters per second. As a result, you and the scale are falling at the same rate. So the scale, nothing is holding scale, so the scale is not holding you in order for the normal force to exist. As a result, normal force will not exist, is going to be 0. As a result, the reading on a scale is going to be 0, then you're going to feel weightless. Let's illustrate the apparent weight with an example. A student with a mass of 55 kilograms stands in an elevator that accelerates. Determine the student's apparent weight, or a normal force, during each acceleration. A. Elevator accelerates upward at 2 meters per second square. We draw a free body diagram. So Fg and Fn is moving upward, so that is acceleration is up and positive direction has to be up. So it's a y-axis is accelerating, so that means F net y is equal ma. Then F net y is equal sum of all forces, we have just 2, is equal to ma. And now since that we have positive up, Fn is positive, Fg is negative. So we solve for Fn, we move Fg to another side of the equation, becomes positive. So Fg plus ma. So Fg is mg plus ma, we factor m. It is g plus a. And then you plug numbers there, 55 kilogram times 9.8 plus 2 meter per second square. So the answer will be 649 Newton. Now, let's say that elevator is accelerating downward, same rate, just for simplicity. We draw a free body diagram. Now it's moving up, moving downward. So the down is positive direction, which is the direction of the acceleration. And we do the same thing, similar to up. The only thing you have to pay attention to a sign, which is down. So F net y is ma because it's accelerating. And F net y is equal to sum of all forces, is the same thing. Now we have to follow positive direction, which is down. So Fg is positive and Fn is negative, is equal to ma. We can solve for Fn, which is Fg minus ma. So Fg is mg minus ma. We factor m, g minus a. Then we can plug numbers. 55 kilogram times 9.8 minus 2. That is 429. If you take a look, the acceleration upward, you feel heavier, and acceleration downward, you feel lighter than normal. But what is normal? A student normal weight is when there is no acceleration, when F net is 0, when the forces are balanced. So that means, based on the first Newton law, the student is moving at constant velocity or not moving at all. So to solve it, as always, we draw a free body diagram. We have two forces, Fg and Fn. Since that is in equilibrium, we just keep it traditional, positive, up. Then we apply first Newton law, not second, first Newton law, because F net is 0. So F net y is equal to 0. That means sum of all forces is equal to 0. So Fn and Fg has to be 0. Then we follow the positive direction, even in the first Newton law. So if we follow the same steps, we will never make mistake. So Fn is positive, Fg is negative, is equal to 0. So then we move Fg to another side of the equation, becomes positive. And we know that Fg is equal to mg, and we have m and we have g. So we plug those numbers and find the Fn is 539 Newton. So that is a normal weight. That is a force of gravity without acceleration. Okay, so next one, what will happen if the student will free fall? Let's see. We draw a free body diagram as always. So we have two forces, Fg and Fn, and acceleration is going downward. That will be a positive direction. So we follow the same step. Fny is equal to ma. Why? Because it's accelerating. It's a second Newton law this time. So F net y is equal to Fn plus Fg. Those are two forces. Is equal to ma. Again, we follow the positive direction. It's down this time. So Fg is positive. Fn is negative. Is equal to ma. And acceleration is always positive. We keep it that way to make it easier and not confusing. And Fn is equal to Fg minus ma. We know Fg is mg minus ma. And we can factor m, and what is left there is a g minus a. Then we plug numbers. Thing is that g is 9.8 and a is 9.8. So it's 0. 0 times 55 is 0. So that means the normal force is 0. So although we draw, and we did the right thing to draw a normal force, in a free fall there's no normal force because nothing is holding anything. Everything is falling at the same rate. So that's why it's exactly what we actually mentioned before. There's no reading on a bathroom scale, because, or no tension on an elevator cable, or no normal force on a bathroom scale holding you, or or an elevator floor holding you, because everything is falling at the same rate. So that means no one, nothing is holding. Now it's your turn to do some practice with apparent weight. Rope A is tied to block 1 and rope B is attached to both block 1 and block 2. The mass of block 1 is 4.2 kilogram and the mass of block 2 is 2.6. You lift both blocks straight up. Calculate the tension in the rope when the blocks moves at a constant velocity of 1.5 meter per second up. B. Accelerate at 1.2 meter per second square up. And that's it for today for section 2.2. I hope you enjoy it and learn. Have a good one.